Hello friends, welcome you all to the 38th lecture on function analysis and its applications. In this lecture, we will discuss the complete orthonormal sets. This is the content of today's lecture, complete orthonormal sets. Definition of complete orthonormal sets. Let S be an orthonormal set in a Hilbert space H. S is said to be complete if there exists no other orthonormal set containing S. That is, S must be the maximal orthonormal set. Thus, an orthonormal set EI in Hilbert space H is complete if it is not possible to adjoin a vector E to set EI in such a way that set EI and E is an orthonormal set properly containing EI. Okay. Theorem. An orthonormal set S in Hilbert space H is complete if and only if for any x belonging to H such that x perpendicular to S, then x must be 0. Proof. Let S be complete and x be non-zero vector in H such that x perpendicular to S. Then this set S union set E, where E is equal to x upon norm x, is an orthonormal set properly containing S, contradicting the maximality of S. Hence, x is equal to 0. Conversely, so let us suppose that x perpendicular S implies x is equal to 0. If S is not complete, there must exist some orthonormal set S dash such that S dash containing S properly. In this case, let x belonging to S dash minus S. Since norm x is equal to 1 and x perpendicular to S, x not equal to 0, contradicting the given condition this. Okay, here x is equal to 0, but this x not equal to 0. This is the contradicting the given condition x is equal to 0. So the assumption that such an orthonormal set S dash exists is false and S must be complete. Okay, this completes the proof of theorem. For example, let in the Hilbert space L2 the set E1, E2 and so on En dot dot dot, where En is a sequence with 1 in the nth place and 0 elsewhere, is complete orthonormal set. Okay, so this is usual meaning of E1, E2 and so on En, that is En equal to 0, 0 and so on 1, 0, 0. This is at nth place. 1 at nth place. So, explanation. Let set E1, E2 and so on. If x is equal to xn and y is equal to yn in L2, then inner product xy is equal to summation n is equal to 1 to infinity xn yn bar, and norm x square is equal to square root of the summation n is equal to 1 to infinity mod xn square. Okay, this is the well-known definition of L2. We know that S is an orthonormal set. To show that it is complete, x perpendicular S implies x is equal to 0 by theorem 1, by this theorem. Now inner product of x E1, okay, E1 is this, at first place, that is 1. E1 is equal to 1, 0, 0 and so on. So inner product of x E1, x has x1, x2 and so on, xn and so on. So inner product of x E1, okay, so x1 into 1 plus x2 into 0 plus and so on, xn into 0 plus and so on, that is this. This implies that x1 is equal to 0, okay. In similar manner, we can prove x perpendicular E2 and so on x perpendicular En will give x2 is equal to 0, x3 is equal to 0 and so on, xn is equal to 0 for all n. Hence, x perpendicular S implies x is equal to 0. So, x E2 equal to, here x is x1, x2 and so on, xn dot 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 and 0, 1, 0 and so on. So this is x1 into 0 plus x2 into 1 plus x3 into 0 plus and so on. Okay, that is x2 and this inner product is equal to 0, that is 0. Okay, similarly x3 is equal to 0 and so on, xn is equal to 0. So x equal to x1, x2 and so on. So here x1 is equal to 0, x2 is equal to 0, that is vector x is equal to 0. Okay, therefore orthonormal set is complete. Next theorem, let H be a Hilbert space and let EI is an orthonormal set in H, then the following conditions are equivalent to one another. First, set EI is complete. Second, if x perpendicular to set EI, this implies that x is equal to 0 vector. Third, if x is an arbitrary vector in H, then x is equal to summation I inner product of x and EI into EI. Fourth, if x is an arbitrary vector in H, then norm of x square is equal to summation I square of the modulus of inner product of x and EI. Proof first to second. Suppose first is given and we have to prove second. Okay. So here it is given that the orthonormal set EI is complete, because we have to prove first to second. In first, the orthonormal set EI is complete. Suppose that x perpendicular EI. Okay. Now we have to prove x is equal to 0 vector. Suppose it is not, then x perpendicular to vector EI and x not equal to 0. Write E is equal to x upon norm of x, which is a unit vector, such that by cross multiplication norm x into E perpendicular to EI. Okay, putting the value of x in this, norm x into E perpendicular to EI. We know that if alpha x perpendicular to y, This implies that x perpendicular to y. So here norm x and scalar. So norm x into E perpendicular to set EI, that is E perpendicular to the set EI. Meaning of this is inner product of E and EI is equal to 0, so that set EI and E is an orthonormal set which is properly contains EI. It means that set EI is not complete orthonormal set, which is a contradiction. Hence, x is equal to 0. Okay, so it should be 0. This is 0 vector. Finally, x perpendicular to EI, this implies that x is equal to 0. Second proved. Now, to prove from second to third. Okay, suppose second given, we have to prove third. It is given that x perpendicular to set EI. This implies that x is equal to 0. Let x belonging to H be arbitrary to prove that x is equal to summation I inner product of x and EI into EI. Taking y is equal to x minus summation I inner product of x and EI into EI. Now, inner product of y EJ. Y is this. So, inner product of this and EJ. Applying the property of inner product, that is inner product of x and EJ minus inner product of summation this and EJ. Okay. So, summation x and EI as scalar alpha. So, we can write the outside of the inner product. So, meaning of this is inner product of x EJ plus inner product summation I x EI EJ. Okay, so this is a scalar. So we can write the outside of this inner product. That is, we have this into EI into EJ. Okay, so expanding this, I is equal to 1 to infinity. And also we know that if inner product of EI EJ is equal to 0 if I not equal to J. And inner product of EI into EJ is equal to 1 if I is equal to J. So expanding this, so sum of the infinite term, all terms different from I to J, except one terms I is equal to J. So we have this inner product of x and EJ minus inner product of x and EJ. Okay. So at jth term, this is EI into EJ is equal to 1 and it will be x EJ and other will be 0. That is this. And this is and this cancelled out. That is 0. Okay. Hence, inner product of y into EJ is equal to 0. It means y perpendicular to set EI. This implies that y is equal to 0. Okay. As second part of this theorem. So y is equal to 0. Here y is this one. It means this one is equal to 0. That is x is equal to this. Hence third part is proved. Now, third to fourth. Third is given x is equal to summation I is equal to inner product of x and ei into ei. To prove that norm x square is equal to summation I of square of the mod of the inner product of x and ei. By assumption, here x is equal to this. Okay, we know that norm of x square equal to inner product of xx. Okay, so x is this. So we can write norm x square is equal to inner product of the summation I of the inner product of x ei into ei and x. Okay, so this is as scalar. So it will be outside the inner product after expansion. So we can write this equal to summation I inner product of x ei into inner product of eix. So this can be written as conjugate complex of the inner product of x and ei. Okay, so this can be written as like this. And we know that z bar is equal to mod z square. So this can be written as summation I of square of the mod of the inner product of x and ei. Hence, fourth proved. Now to prove fourth to 1. If norm x square this is given, then we have to prove ei is complete. Okay, so it is given that norm x square is equal to this. Suppose that ei is not complete, so that it is a proper subset of an orthonormal set ei and e. Okay, consequently e perpendicular to ei, so that inner product of e and ei is equal to 0. Okay, suppose x is equal to e. Here norm e square is equal to, this is a summation of I of the square of the mod of inner product of x ei. Okay, so x is e, that is this one, and inner product of e and ei is equal to 0, that is norm of e square is equal to 0, or norm e is equal to 0, that is e is equal to 0 because norm x is equal to 0 if and only if x is equal to 0. That is here e is equal to 0, but e is unit vector. Okay, so norm e is equal to 1. So 1 is equal to 0. Is it possible? No. So this contradicts the fact of that e is unit vector. Hence, set ei is complete. In this lecture, we have discussed the complete orthonormal sets and related theorems. These are the references which have been used in this lecture. Function analysis, Dover publications, written by George Beckman and Lawrence Naresi. Second, introductory function analysis with applications, John Whaley and Sons, written by Erwin Krejcik. Third, function analysis, New Age International Publishers, written by B.V. Lemieux. And fourth, function analysis, Tata McGraw-Hill, written by Waterrudin. Thank you.